Moshi Moshi! Hello! Today we're going to be talking about something that I had actually recorded earlier, so I don't think there was like more than one person on anyways, but I do want to make sure there's something here for posterity's sake. Because it is a topic that I come back to more often lately than I thought I really would, to be honest. It kind of surprises me. Specifically, it's this idea of sort of scaling out your use cases of CMake and Git submodules for modern C++ projects in a way that gives you something that is, while it feels patchwork at first, surprisingly effective in terms of modernizing how packages are managed and how, effectively at least, and how the modern C++ infrastructure can work in a fairly reusable and reusable way that not just reusing specific elements, but actually being able to ensure that this tool will build here and that tool will build there, and you don't have to worry as much about platform dependencies, etc. You have no matter what the build chain is, or well, you'll see. Specifically, at the root of the problem is this idea of, well, how do you structure a C++ project, right? What goes into a C++ project? And this is, C++ programmers are a little bit like cats. They all want to go in different directions, and I'm one of them. I should know that. So there's been some attempts to say, oh, this is the canonical layout of a C++ project, right? So here's an open standard example. Here's one from another blog post. This is a little bit more common, actually, in my experience. Having different bin, lib, doc, source folders, etc. Don't ask me about Spike there. And of course, if you go on somewhere like SOAR or Stack Exchange, there's hundreds and hundreds of comments, but we do it this way. No, you have to do it this way. It's a very contentious topic, right? And just to throw out another one, this one's a little bit more Pythonic, but pretty standard. Breaking out, to the degree that any sort of standard exists here. A particular folder structure with source trees and sort of meta files and other things. There are some good takeaways in my experience from Python, but really at the end of the day, the main problem here is just the fact that there's no, by definition, by purpose, no specific language features that are supposed to support any of these things. So with great freedom comes great, I don't know, however you want to make that analogy. Every C++ project, though, wants to be special and wants to pretend like theirs is the only way to do it. So really what you need is just a set of tools that let you build regardless of what the structure is. Let's assume for a moment that it's never going to happen, that it's hopeless, and that the best you can hope for is just simply be able to build a C++ project, right? But how do you do that in a way that lets you pull in different useful pieces and elements in a reusable manner? So I'm giving C++ a pretty bad rap here, of course, but if you've ever messed with like Python packaging standards, those seem to brutally change every 2-3 years or so. It's getting a little bit better, but if it weren't for like editable pip installs, I don't know how I'd be developing on a day-to-day basis. There are theoretically package managers for C++, but let's not pretend like everyone's going to start using Conan, right, or VC package, right? They're decent tools. But if you're going to be using someone else's code, the chances that your code and their code are going to be using to be able to communicate in the same package manager for the same platforms is practically zero, right? So let's think about how this could be structured with some of those core reusable technologies without having to enforce specific standards or folder layers or whatever. So there's a couple of heuristics that go into this, or at least priorities, right? It helps to be able to define like what goes into a package, specifically setting an upper limit so that you know that if there's this much more than this in a package, it should probably be broken up. Setting an upper limit on the complexity in particular, it not only makes it easier to just look at the folder structure and understand what the relationships are, which is particularly problematic in C++ because there's divergence between the logical, like the file and folder structure, right, and the logical structure in the include paths, etc. And the symbolic representation within the code itself. But it also makes it easier to understand what CMake is doing. Let's assume we're using CMake, which is probably a pretty safe assumption, given the topic given this topic anyways. If you're looking at include statements in the source code and you're trying to map that to how does CMake, trying to figure out where those import libraries come from and where these headers come from, are they from there or from this copy of that source dependency or that copy. keeping it consolidated helps you understand exactly what CMake is trying to pull in to build a package at any given point in time, and that's a big help. There's also this idea from Python, like one of the most beautiful things about Python, and we can trash talk it a lot, but is this isomorphism between sort of modules and packages on one hand, so how the symbolic symbols are actually represented and imported and managed like within the source code, right? And the actual files and folder structure. So a module is a Python file. Like, tick, that's it. That's what a module is. And if you look at a language like Zig, there's all sorts of, maybe that's a little unfair because they're still trying to figure it out. Like this idea of a module tends to be so abstract and so different across use cases that it's practically borders on useless. But in Python, it's simple. It's a file, so it's a module. Same idea with packages. A folder, maybe with an init or something like that, is a collection or a set of modules. Like, hey, there's a namespace for those. It's wonderful. That isomorphism is just beautiful, and when you go too long in C++, you really start to miss it. Namespaces are nice, so maybe we can use namespaces to sort of not enforce, but gently suggest or guide some sort of relationship between those two structures. Platform agnostic builds are simply a must. We have to be able to do it, and that means CMake, pretty much. Some people, well, actually, it's a pretty common complaint. Love to critique CMake for being like, okay, well, you have to learn a C++ language, and then you have to learn a CMake language. Like why learn one to build the other? Like two languages, big headache. I find that if you learn sort of a minimum of use cases, like 10% of the scope of CMake, you can get 90% of what you want done. It will cover. It's worth learning some of the more common commands because it will cover so much of what you want to do and give you so much of value out of it. I don't know that much CMake, but being able to make sure it's usable and to be able to apply it on a day-to-day basis is pretty straightforward. Just learn a few basic things. We also need to figure out dependencies. The dependencies being a big issue, as you can probably figure out from the title, like we'll probably go with the C submodule or Git submodule approach here. That means we're leaning on Git for a few things, but that actually ends up being nice. So we don't need to worry about specific version compatibilities. We have commit hashes for that, right? We don't need to worry about tracing where the dependencies are come from because the Git knows what the upstream repository is, etc. And then CMake pairs with that fairly nicely because it can recurse into submodules to build them and then extract out the symbols at the top level to compile the program as a whole. There are a few, we won't go over them today, but there are a few subtle tricks here to make sure, like if there's a, in your directional acyclic dependency graph, if A depends on B, which depends on C, and A also depends on C, to make sure those things aren't redundantly included. Just some like useful subroutines include CMake, but it is possible. It doesn't make it impossible. We also want to avoid sensitivities to too many other contexts. Pre-processing is a big problem here, of course, but environmental variables, let's try and avoid too many of those beyond resolving like system libraries for includes. We should be able to implement and realize and resolve most of that within the CMake itself. We don't want to be leaning on the source for that. And lastly, we want to sort of eliminate the redundancy of information because it's so easy to conflict. Like I say the package's name is here, is this here, and that thinks it's that there, and then they get out of sync, right? Being able to reuse some of that information would be great. So let's get started a little bit here. Let's say we have basic CMake, right? We'll toss a little placeholder. Usual. Just make sure it's resolving system libraries. Okay, so here's sort of the minimum template of CMake, right? You need to declare a specific version. Give yourself a project name. Let's do this just to keep it reasonably consistent with our folder structure here. This isn't strictly speaking necessary, but as more and more people start adopting or at least confusing sort of the modern C++ features, it helps to declare up front exactly what your expectations are for what features are going to be available. I can type as well. And lastly, in this case, we need to associate an executable entry point. Another tip I'd recommend, especially when you're looking at something with syntax highlighting like this, whenever you have a path, like actually treat it as a string value. In a declarative language like CMake, that's not strictly speaking necessary, but it really helps to be able to look at your CMake and know, like, okay, that's a path. I see it highlighted as a string. Therefore, I need to know it resolves this way or that way, or that it's not some variable reference. Easy to confuse those if you're not careful. So then we'll add ignore, right? So I'm on Windows, of course. This process wouldn't be too different than anything else, but if you are in Windows, strongly recommend you consider the command line tools, and then adding those to your path, looking at include, lib, and of course the path for the binaries for CL, lib, MS build, and CMake, and just making sure the executables are all there. You don't have to use the batch files that are built into that installer, and you definitely don't have to install like the full Visual C if you're about licensing or anything like that. Like the command line tools, especially with CMake, will get you. It'll take you quite far. So let's do our standard build here. Make sure that's in ignored. Build. Are we good? Did I miss anything? Nope, we're good. Okay, so we have sort of a starting point, right? We can start scaffolding on. Happy with that. Now let's talk about dependencies. I mentioned submodules. We're going to kill two birds with one stone here. We're going to add a dependency, and we're going to use that dependency to help us flesh out like a testing framework. So let's add Google test here. I love how VS Code says, hey, this is submodule. Sorry, something about that. Okay, so now we have that. There are a few other adjustments we need to make to our CMake. Some of these are unique to gtest. Not all of them are required anytime you add a dependency. And especially for like community dependencies that aren't system specific or giving you some specific system function like testing. Most of these are not, strictly speaking, something you have to do for any dependency you might have, like SDL or what have you. Typically, when you have a dependency, you're going to need to do a couple of things. Two specifically, adding the subdirectory, using that subdirectory directive in CMake is basically the recursive step. In this case, there's a special flag to say we actually have testing too. Let's go ahead and add a tests folder with some tests. We'll just make sure that addition is working. Wouldn't that be nice? All right, so we need to include gtest here. Gets up. In keeping with that idea I mentioned earlier of using namespaces to give you sort of that nice isomorphism between symbolic structures internal to the code, we're going to use some namespaces for that. In Google Test, you just say there's a test suite, and here's the test I'm defining. There, of course, are a number of assertions built in. And then, if we want to call this directly, we need to define an entry point to be able to hook in the ability to run the tests if they aren't being called from a higher level test suite. All right, so there's a test, right? But we actually haven't hooked this into any sort of build step yet. We just made sure that the dependency is being built. So now we need to go back to CMake and make sure that we can add these tests to the build process for our top level project. And to do so, we're going to use a handy dandy function here. Some of this is a little bit convoluted. It's going to make more sense when you see how I use it. But basically what we want here is a function that's going to let us easily hook in arbitrary test modules that we might add as we flesh out our package here. So any other files we add in this test folder, we just want to be able to say, hey, this is tests, add it. Here's a new test module. Otherwise, each of these lines represents something that we would have to copy and paste over and over again every time we wanted to add a test. This way it will be much more streamlined. I think I got it there. So now, each time we have a new test module, we can say add. So we said equations addition, test addition. So you can see what I meant here by using paths as strings. You can tell that, okay, there's this symbolic reference, so this is just the symbol for that test, or the name, and then there's the actual path, right? You know what the path is and what the other arguments are. So if we go ahead and build that now, we'll see a few things change. Including the fact that it doesn't build. What did I do wrong? Google. All right. So the build infrastructure setup. No, let's actually compile everything. And then CMake also has this ctest executable, which is pretty nice. You say there's this test directory. I had this configuration. We'll go through and run all of the tests that you compiled that were flagged as part of that. So you can see here, surprise, surprise, addition works on the computer. But you can tell how this would be fairly scalable. And at this point is something that you can sort of start building out incrementally, right? And this isn't just true for testing. This is true for any submodule. This is probably how you do it again, and it would be much less complicated because you wouldn't need all the sort of the testing overhead here. All right, now let's talk about actually structuring the library. We have sort of the tools and the integration pieces down, but there are some nice ways I've found to sort of flesh out step by step the internals, especially given the heuristics that I mentioned earlier. So let's say we have a library header here. What did I call this? Yes. This is a little bit controversial. I find it's actually very helpful to only use one header for a given package. You only have one thing to include, and that's particularly nice for other packages that may be consuming yours. They don't have to figure out, like, where is this defined, where's this defined, where's this defined. But it also makes it much more streamlined when you're writing specific implementations for each class or prototype or anything else that's defined in the header. Because you can break those down into individual modules if you like, but then you only have one artifact to share along with the build binders or what have you. And you only have one artifact to include from each of those modules. So you don't have to worry about, well, did I include this one but not that one? What's the internal dependency there? Like, anything internal to the package is exposed to the implementations that you're writing out. And while I did say I wanted to avoid preprocessors, Pragma is kind of a must. So let's using that. So we're going to define, this looks a little weird, but since we want files for namespaces, you don't have to do it this way, to be honest, but the implementation files will have some sort of food class, right? And then there may be other methods associated with that that aren't actually part of the class definition. And this is just a basic polymorphism exercise at this point. I put that in the wrong place. Still trying to use the whole talking and streaming coding at the same time thing. So my apologies if that's not making a lot. So if you've done like, you know, we have a class and inherits from another class, right? So this is sort of the basic declarations that we may want to share anytime we move this library around or give it to other people. So now we actually want to pull into these specific implementations, and this is where it might start making a little bit more sense. So we have these, right? And there's our one header. Instructor. Again, it's kind of a cutesy example, so don't take it too seriously. Now we have something to be overridden. We can go ahead and add our other module. So cout's not defined. Is that because all right, that should do it. And then we had another module here. Again, just want to include. Give us something to override. I keep on messing this up. Did I give that a bad scope? Inaccessible. Thanks, Ann. Yeah, made it private. Well, that was a mistake, yeah. Then we're going to override this behavior just because we want to. First off, you can't need a cookie just once. But at the end of the day, we also just want to override something. I think we're ready to build now. So let's go back to our top level build. We're going to have, pretend for a moment this is a test. Now we should be able to, yeah, there we go. Yay, we have some food. We'll verify everything got overridden. And let's give it a shot. Okay, so there are a few things that we need to adjust now in the CMake file. In particular, we don't really care about, this main is just sort of a test. Let's ignore the static library build case for a moment and just pretend that we just want to link all this stuff together, right? So for each implementation, you need to compile it. They'll include their own headers, of course, but you have to add those as a list to the executable for the project. I find it's very helpful when you know you're going to be extending that set of lists to put it on a different line just so you can see an enumeration instead of stretching out all the way to the right. It's also a lot easier to copy and paste and move things around. So let's see. How are we looking? Let's break this up. This is the basic project definition, right? And then we have some sort of, you can think of it as a primary build target. Theoretically, you can have other build targets for a given project. Let's say there's an executable entry point. for this project. Okay. This is basically some one-time test configuration, so or setup, right? Just specific to Google Test. We have some sort of a hook, and then we add each test module, right? So as you develop out the package, what you're doing is, you might have additional implementations, and then there's probably going to be some additional tests, but everything else actually stays relatively consistent here. This scales out in an incremental way quite nicely. So let's go ahead and make sure that I didn't mess up too badly here. Another reason I like this approach, by the way, if you're noticing I'm using a build folder, is one of the things that always irked me about Python is the fact that your meta files, like your metadata, is at the top level and your source is like further down in some replicated name of a folder structure. It just always seemed kind of redundant and sloppy to me. I would much rather have sort of the metadata live in the secondary folders where I can ignore them if I want to, and just have the source there at the top. It makes it much easier to extend and adapt if you have an existing code base, because that tends to be just blobs of source files and headers, right? You don't have to worry about how am I going to reshuffle these, how's the folder structure going to change. You can add what you need to as you're extending the meta information beyond the top level CMake and the .git files, however you need to underneath that. Okay, so we were able to set up the build configuration. Let's make sure this doesn't completely break when it compiles. Hey, look, everything built. So now we have, well, you look at that. Okay, so we have some interesting ideas here that, again, these aren't fixed requirements, but it does make things nicely scalable and incremental. But let's pretend we actually wanted to share this. So let's assume for a moment that if you're writing a program with an entry point and executable, what you're effectively doing is providing a way to call into a specific initial state and then subsequent behavior that might be defined anywhere, particularly in the static library collection of static libraries, or any library for that matter. But at the top level, the executable package is probably mostly going to be focused on handling things like parsing arguments, setting up the calls that it needs to make. And the actual logic, or maybe the game loop, or what have you, is going to be somewhere a little bit deeper, maybe one or even two layers into your dependency tree. And that's where your core algorithms redefined, or anything else that's sort of the sophisticated meat and potatoes of a project. So what that means is if we wanted to start sharing this as a library, it's surprisingly straightforward. So we had an executable here. We said this was an executable. Instead, we're going to say this is a library, and it has all of these things. So we're going to remove our entry point here. Let me stash this. Get ready for libraries. Right. So we changed that call, and now it's a static library. So, are you serious? Like, that's all you need to do to sort of wrap up the implementation and all of your header and everything, to make sure that it's at a point where it can be shared. And if you don't believe me, let's clear out the previous artifacts and go ahead and build this. Let's see what it made. Do you look at that? So this ends up also being a fairly nice way to make sure that what you do write is fairly easy to share as some sort of package or library that can be hooked into or compiled by other tools. That's a very nice way to structure and collaborate on applications too, by the way. There are a few other things that you could do, a few other directions you could go in from here. Obviously, there's no README here, right? That should be part of a standard folder structure. Maybe a license file. We could define some sort of doc building pass. Theoretically, you could do that in CMake. My personal preference is to do that as part of like CI, so you're not just constantly trying to rebuild docs in your machine. It should be, part of the integration process taking place somewhere on a server. And same thing with sort of, installation of other includes or libraries or binaries that are needed outside of the submodule structure. But this is a nice enough approach that I actually have this as a reusable. If you've ever used a dget, let me pull this over here. So I can use the dget command to just instantly use this as sort of the scaffolding for any of my initial projects. Um, so I'd say something like dget, then URL to this, and maybe pass in some template variables if I really want to. And that's sort of my initial, I don't have to worry about any of the boilerplate. And there's not much here anyways, but it's a nice way to get going fairly quickly. Then the other nice thing here, of course, like if you, again, just like the S for submodules in VS Code, like you could look at GitHub and see, hey, that's a submodule. I don't know why that gives me warm and fuzzies, but it really does. Let's take a look at something that's a little bit more complicated, because obviously this is academic. This is, we were literally defining cookie classes. Here is a numerical mathematics library that I've written, largely based on a really good textbook I used in grad school. So you can tell it's using eigen as sort of the numerical modeling piece for matrices and vectors, and their operators, and then there's implementations for each of the the namespaces within there. But if you look at Cuban, oh, it uppercased on me. There we go. So here's the header. And you can see everything that's defined within this package. If you want to share it, you share the static library or whatever, and the header, and you just include the header. So there's sets of exceptions, there's namespaces for under fundamental operations and system solvers and ODs, etc. And all of those are defined in their own modules, but there's just one nice header. I'm not going to harp on that too much, but it does work out pretty nicely. The only other thing I'll share here is like what the CMake looks like as you start fleshing that out. This is exactly the same. Right. This is a much more sophisticated use case, but you can tell how sort of incremental it was to start from that. Each time there's a new module, you say, well, that's part of the library too. There you go. And then each time there's a new test, and I typically have one test module for each implementation module. It's a fairly nice way to organize it. I say, okay, well, now there's a new test module too. And you can do the same thing that we saw with the console sign, just CMake build, C test, but done. And then that can be included as a dependency from really anywhere at the end of the day. So this is a nice enough pattern that I'm confident saying this is probably how I'm going to do 90% of my C projects going forward. One interesting contrast is Zig, because I've been trying to do more Zig lately, and there are some trades there. One of the nice things about Zig, of course, is the fact that you have not just compile time, but you have like the actual build script for compiling, right? I've gotten to the point where I'm not sure that was the perfect idea. I actually kind of enjoy having, a static declarative specification for the project build. Like not everything needs to be scripted or have its own proprietary data structures, what have you. Especially as I mentioned, like if you know a little bit of CMake, you can go a long way. That's fine. Minimization of preprocessors is great. Mixing up comp time can be powerful, but kind of confusing sometimes. But there was one other thing I was going to say about the Zig contrast. Huh. I can't remember what it was. Well, is it modules? Yeah, they're still trying to flesh out the modules piece. So the modules and packaging piece. As I mentioned, like the definition of what is a module, like over the past year, has changed several times anyways in the Zig ecosystem, but they're still trying to figure it out anyways, and let's not pretend like C can tell you like out of the box like, what a module is supposed to be. So I don't know. I think that probably works. Maybe you learned something from this, maybe you didn't, but as always, thanks for stopping by, and I will put this up when we're done. Cheers.